Hi, this is Sholey Physics, episode on a magnetic field of a current element and the Biot Savart Law. Yeah, that's kind of how you say it. It's not Biot Savart. It's just one of those things. It's pronounced Biot Savart. Got it? Good. So this episode is brought to you by the planet, the dwarf planet Pluto. See, take that. Yeah, Pluto's this, it has a special place in my heart. And down in the description for this video, you're going to see a link to one of the best Planet songs ever. Me and my family really like it. My wife found it. It's really neat. So anyhow, we're going to be first looking at this apparatus here, and it has a current carrying element, this copper wire, with some compasses placed around it to take a look at the magnetic field produced around this current carrying wire. And this is a hop, skip, and a jump from our last lesson, talking about the magnetic field produced by a moving charge. You might recall that mu naught over 4 pi q v cross r hat all over r squared. Yeah, that one. So that whole direction that's involved, the direction of the magnetic field around the moving charge, is going to be demonstrated here, but instead of a single charge, we're going to have a flow of positive charge moving from the right to the left and then coming up and out of the screen here. I'll show you how this thing works in a moment. In this demonstration, I'm going to take this copper conducting element that's supported by this kind of plastic base here, and I'm going to place several of these compasses of questionable quality around the wire to check out the direction of the magnetic field. Of course, this isn't going to indicate the magnitude of the magnetic field, but it'll definitely show the direction. So in the next segment, I'm going to orient the platform like this. I'm missing a little foot there, so I have my Cheerio I'm going to put underneath there. It keeps it stable. Cheerios have multiple purposes. And then I'm going to place the compasses around the wire up here and a large compass down here. It's going to be oriented in a way that you can see this more clearly. The next part is I'm going to connect one side of a current source. Got a big current source down here. Think of like a battery, but it's plugged into the wall. It's kind of nice. So I'm going to connect the two ends right there and there. That'll conduct the current this way through the wire and up that way. So see that in a moment. Here you can see all of my compasses facing more or less north. They're rather cheap compasses, so I do get mixed results with this one, but right now the current is off. And from this perspective here, you see the current element, the copper element, and it curves down here and comes up towards you. So you're seeing this current element along its long axis. So what we should see here is a change definitely from these compasses. They're all more or less pointing toward their north, and there's a large compass down here. I think some of them are a little demagnetized. We do get some mixed results here, but what I'm going to do here is just start it up. Here's the current, make it flow. And there we see the DL cross R hat happening there. We see the direction change according to the right-hand rule. So if you take your thumb and point it kind of out of the screen from this point up and just curl it around sort of like that, okay? Your thumb pointing towards that in the direction of that element. Then on this side, the direction of your fingers curled is the direction of the magnetic field. Then we have the magnetic field going this way, and then this way on this side, and then kind of to R up and left here. So all the red parts of the compass are pointing in the direction of the magnetic field. The large compass is deflecting to the right somewhat down below. If you do the right-hand rule, thumb going this way, then your fingers will curl down underneath that current element so that they're pointing this way toward the bottom right part of your screen. I'm going to turn the current off, and sometimes, oh, there we go, takes a moment. Just tap that a little bit, and the compasses tend to return towards their magnetic north direction. And just for one more go, current back on. You can see all those rotate to go along with the Biot Savart Law in that direction of magnetic field. So in the last lesson, I introduced the magnetic field that's produced by a moving charge, and that's linked at the end of this video. Today, though, we're going to look at how the charge that's moving through a current-carrying element produces a magnetic field. Now, if we just consider this in terms of our last lesson's discussion, if we look at a single charge moving along, let's say drifting through a wire, that's represented by this positive charge right here. This would be the positive hole in a wire. It would produce a magnetic field. That motion of that charge would produce a magnetic field around the wire somewhere. So if we look at the position above and below that moving charge, what direction, according to the right-hand rule, would it be moving in? Well, we'd have to define an R. So the velocity is to the right, and the R to this top position would be that distance. So there's the R up to that point. So if we look at the angle between them, it's 90 degrees perpendicular, and that's good. So according to the right-hand rule, we'll take the velocity going this way and face our palm towards the direction of the next vector R, which is up on the screen. So I'm going to curl my fingers that way. Therefore, my thumb is the direction of the magnetic field at this point. It's coming up out of the page. So I'm going to put a dot there to represent the arrowhead pointing towards us. And what about this point down here? The R vector goes from the current carrying, the moving charge, I should say, the moving charge, down to this point. So if that's the R for this position, what direction is the magnetic field down there? So we take our hand and we got to now turn it so that the palm is facing the direction of that R, curl the fingers that way, and now my thumb is going down into the page. So down here the magnetic field faces downward. So if you look at this orientation, there's another right-hand rule you can use, which I think is a lot easier to use when you're dealing with a wire. And if you've ever been to Busch Gardens, it's like in Williamsburg, there's this old, I guess it's an old show, and I haven't seen it there in a while, but there's this big place called the Festhaus in Germany. It's part of Busch Gardens, the old country. And in the Festhaus, they would have this oompa band we like listening to, and they always raised up their mugs and taught us that this tradition is to hold up the mug and say tiki taki, oi, 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 or something like that. I forget what it is, but imagine you're holding a mug with your right hand. It's got to be the right hand, okay? And now your thumb is going to be the direction of the moving charge, or in this case, for the rest of the lesson here, it's going to be the direction of the current flow. And now look at your fingers. They're curled kind of like that. I guess kind of point towards you. So if the current is flowing along my thumb, the curl of my fingers would be the direction of the magnetic field at that point. So below this current carrying wire, or the direction of the charge flow, below it, the magnetic field is going this way in the direction of my fingers. And above it, if I turn my hand like this, above it, this is the direction of the moving charge. Above it, the magnetic field is going this way. And on the side, it's going down. And on this side, it's going up. So if you look at that, that'll agree with this diagram. If the current flows this way, then above it, the magnetic field is pointing up out of the page. And if I curl it this way, I'm off the screen. Then the current flow is down. Below here, it's down into the page. So I think that's just a little easier when dealing with current elements. You can think about, since this is a kind of a three-dimensional object, we're looking at a two-dimensional space, it makes it a lot easier to imagine the direction of that magnetic field. Kind of out of the page here, if we're looking at a magnetic field see up above that paper, like right here, the magnetic field would be going down towards the bottom of the screen. And kind of into the page, if we were on the other side of the wire, it would be going up towards the top of the screen. All right, so we got directions covered here, this V cross B. I hope that was a little bit more help with that new right-hand rule. But now what we're going to do is convert this into an expression involving current instead of a single moving charge that has a velocity. So current, of course, has a drift velocity. And I could go back to the definition of drift velocity and work out all these parts. I think it's just a little bit more, not a little less straightforward than this way to look at it. So instead, I'm going to rewrite the expression from yesterday, but instead of Q and V, let's think about that little combination of charge and velocity. And I think we saw a little bit of this from the force on a moving charge lesson. You see that Q is related to current. Current is a rate of charge, a Q over time, a Q over T. Well, right next to this, and as a product, we have Q times V. And velocity is a rate as well. Since it's the charge that is drifting with a velocity through this current carrying element here, we would have a positive side over here and a negative, of course. We'll mark that. Then we might instead write this as a Q. For some reason I put a D there. As a Q, actually I know the reason, times, and velocity is a dx dt. All right, now this is just kind of rough looking right now, okay? And keep in mind that that's a vector and r hat and r squared, so we'll keep all that stuff in there. Now if I look at this expression, it's not a single charge that's moving through a segment here, but a little piece of a collection of charge, dq, a little slice. All right, so this q is a collection, an infinitesimally small amount of charge that's passing through this segment of the circuit, of the current carrying element. So this is really more of a, rewrite our first part there. We've got really a dq times dx over dt, but I'm also going to move this dt over to underneath that dq because we're going to relate that to the current flow. And what's left is a small section of the wire. And if this is the length of the wire, I'm going to call that small section dl to go along with that little tiny charge dq. So instead of a dx, like a horizontal direction, we're just going to go at a little section along the length of the wire, dl. And the L has a direction of the current flow. And that gets crossed with r hat. So finally, what we're looking at here is a dq over dt is the current, I. And we get left with a dl. Now, if you look along this length of the wire, wouldn't charge, a little positive charge that's moving here, wouldn't it also create a magnetic field at this point or at this point? Or what about the charge over here that's moving as well in this current? It would also create a magnetic field at this point and this point. So the magnetic field over here isn't just a single magnetic field from a little piece, it's a little part of the magnetic field from the current flowing through a small part of the length of the wire. Of course, we have the distance r would be the distance from that point, or from that wire, from each of these little points to that moment. So the r does tend to change. You'll see there's a different r from all those little pieces. And we can even look at this piece over here. So it can get kind of ugly. But what we're going to have to do next is sum up all of that magnetic field that contributes to the total magnetic field at this point in space, above or below that wire. But this is the expression we're going to use to do that. And this is called the Biot Savart Law. Or the law of Biot and Savart. Heard it said both ways. My little shout out to Dr. Kramer at UMBC years ago. I got to say, the first several times you said that in class, I was like, what? Because you've got this awesome New York accent, Dr. Kramer. And I just remembered that. It's like Biot Savart Law. I was like, what? Being a Marylander, you know, it was kind of hard for my ear to pick that up. But then I looked it up in the book. I'm like, wow, okay, that's what it looks like. So thanks, Dr. Kramer. Anyhow, we're moving on. This is the Biot Savart Law. And in the next segment, we're going to cover applications of the Biot Savart Law. See you then.